This is my Peltier PID circuit. First of all, the power supply. I only have a single rail power supply, so the positive is supplied from here. It connects together to a split rail regulator. The negative supply is supplied by this battery and an additional 18650 volt battery to get the voltage high enough. The Peltier used is on here. It has a heat sink with a fan. The fan is powered by this separate battery since I can't power it off the 15 volt supply since it doesn't support that, and it would cause, if the fan is too strong, then it would cause too much drain from the split rail supply, which is only designed to supply 1 amp at most. Currently I have 2 multimeters here set up. This one here is reading the set point voltage, so it won't change. And this one here is reading the thermistor voltage, or the voltage from the thermistor voltage divider, which is here. So it can be used to determine what the error value is. The error will be, if you add these two together, you'll get the error value, which is produced at the error amplifier over here. The way the circuit works is there's a 555 timer which generates a triangle wave, a comparator which then turns the triangle wave into a square wave using the output of the final summer as the reference voltage to determine the duty cycle of the square wave output. That output then goes to a inverter and then finally to a MOSFET, since the initial duty cycle will be the inverse of what's needed, and I can't simply swap the inputs around because that would cause range issues with this particular kind of op amp. The first stage op amp is just a follower. It amplifies. Alright, so the first one is just a follower amplifier, which so the first op amp is a follower that simply amplifies and stabilizes the output from the thermistor voltage divider, which is a pull-up since the NTC thermistor is a negative coefficient, so the resistance goes down, I think it was, as the temperature goes down as well. The next stage is the error amplifier. It takes input from the set point, which is connected to this here, or another voltage divider that goes to here, and it determines the difference between the value from the thermistor and the value in the set point. So ideally it would be 0 once it reaches the set point, and once it hits 0 the circuit would stop outputting, or it would regulate the output at a fixed voltage. The one over to the left at the bottom was supposed to be a differentiator, but this circuit doesn't actually need a differentiator. Also, a differentiator magnifies the electrical noise and the high frequency components of any signals or distortions and amplifies that, so it basically caused a massive feedback loop. And the higher the gain of the differentiator, so the smaller voltage difference or the smaller number of volt increases per second, the higher that is, the worse it amplifies high frequency voltage on the signal. Plus also the Peltier doesn't actually change in voltage very quickly and only in one direction, so it wasn't needed. On the same op amp, the next one up is a standard inverter amplifier, which is the proportional stage. It's set by this potentiometer here, and it just multiplies the error value by a fixed value. Currently it's set to multiply by about 3. The next stage over is the integrator. Because I made a mistake, there's nothing on the other side of this op-amp. Anyway, the integrator will develop a voltage charge over this capacitor in proportion to how long, or in proportion to the amount of time that the error value has remained a non-zero value. So whatever the voltage is on the error, it will charge this and build up over time to eventually produce a output. And it will do this in both directions, so it can produce a positive or negative output to oppose the remaining signal. Finally, this here is the summer. It combines the proportional and integrator together. This orange cable here then has the output, which is fed back to the comparator, which is I forgot to mention, a LM311P. This voltage then is used to determine the set point for at what point a triangle wave, it combines a set point and triangle wave to produce a voltage variable duty cycle, which then goes to here. This is the final inverter, because the output, as I mentioned before, is the inverse of what is actually needed for, essentially it would become, it just needs to be inverted. And this here is a voltage divider, has an amplifier as well as a voltage divider and finally a pull-up. Since the inverted voltage will be between 0 and negative 12 volts, the divider and pull-up is required to then turn that voltage from 0 to 12 volts to around negative 1 to 5 volts. This here is a very high current MOSFET, and it drives the peltier. There's a capacitor here just to stabilize the circuit at this point, as this entire thing generates a large amount of electrical noise and has a lot of harmonics and other things, I suppose. Oh, just in case I didn't say, this is with the 555 timer. It has a triangle wave generator on the output, which basically is just a what's it called? It's essentially just filtering the output of the square wave. I'm not actually using one of the pins of the 555 will directly output a triangle wave. However, the voltage offset and magnitude was all wrong, so I wasn't able to use it properly, and I felt like I shouldn't either, since that's sort of cheating and using the 555 as a triangle wave IC. Then we have a pass-through capacitor, and finally, and also a pull-down in order to stabilize it. This part of the circuit here doesn't actually do anything. It was just for testing purposes to simulate a voltage. It's a divider. It's a rail-to-rail divider, or 12 volt to 0 volt, depending on what I needed. It's just a divider here used to generate a fixed voltage output. This mess here is the result of 2 multimeters and a 2-channel oscilloscope. The yellow channel 1 is on this yellow cable. This one here. It is the output of the summer. Then the blue cable, the blue line, is on the differentiator, since the proportional amplifier has an apparent effect on the output of the final set point voltage, the final signal output of the PID, or PI. So at the moment the oscilloscope is set to, for channel 1, 2 volts per division, and for channel 2 as close to 4 volts per division as I could get it. And the time is 1 second to display the full effects of the PID amplifier. So what I'm going to do now is connect the peltier to the battery and it will start going. So at the moment the voltage is rising, and now I'll zoom in here. So as I said, the blue line is the integrator, and yeah, it will change the bias it has on the signal output depending on how much the error is, and in general it will try to cancel out any overshoot, as it will change sides when the error goes from a positive to a negative. Ideally, eventually it will oscillate and eventually turn into a stable, flat line. Also, the value of the output here is feeding the... there is considerable noise on the output caused by the final inverter, which has just compounding output, and the louder, or the harder the duty cycle, or the harder the VCO component of the circuit is running, the higher this distortion is. But since it's uniform, it actually doesn't have any impact on the operation of the comparator. It'll average it out and just cause a slight phase shift in the output. So fortunately, even when it was a lot worse than this, it was still not having any impact on the circuit's ability to precisely control the output. So right now it is stabilized. These two multimeters aren't, they're different brands, so they're going to output different voltages, but they are both, the output here is now stable, it's not changing at all, and it has effectively hit the set point of the temperature equivalent of 4.4 degrees. I'm currently changing the polarity of the peltier now to cause the peltier to heat up so I can do another overshoot test. So now the voltage will plummet as the peltier heats up, since peltiers are bidirectional. And that's enough. And now I'll switch it back. I initially wired it up the wrong way, which is why the red jumper goes to the black cable and the black jumper goes to the red cable. But since they're bidirectional, it doesn't actually matter. So now I'm going to keep the multimeter in focus and show how it behaves. One thing to note right now, that because the ramping voltage is so slow, so the ramping speed is so low, is because the only power supply I had available was a 12-volt battery, and something in 15 volts would have been more ideal. But I also couldn't connect the peltier directly to the power supply, since it would exceed the current capacity of the power supply. Alright, so it looks in this case like it hasn't really engaged the integrator very much. The duty cycle is normally 100%, but now because of this noise you can tell that it's engaged. It's cancelled out any overshoot on its own. The peltier is actually fairly stable as it is, and the integrator is for the most part unnecessary. I would say that it is more necessary the higher your voltage is and the higher your ramp-up speed is. Running it off 12 volts, I'm able to run it at almost any voltage up to its limit. And yeah, right now the integrator settings are actually a lot higher than what they're supposed to be, because otherwise it has no effect that actually shows up on the oscilloscope. I'm going to now set it up again at a lower voltage set point to try and show how the integrator is working more. Alright, now this is roughly at room temperature, and I've set the set point to 3.9. So now I'm just going to show the oscilloscope. It's at 3.7, 3.8, 3.9, so now it should be overshooting. Right now the output of the integrator is clipping. I wasn't able to messing with the gain and the voltage and the actual rail outputs and the amplification all have influences on one another, which makes it undesirable to actually do this. Right now the overshooting is reaching 95 millivolts. That's the extent that it's overshooting, and it'll keep doing this for a while before eventually stabilizing. Normally if the proportional amplifier was turned down a little bit, it wouldn't do this as much, but there was also a risk that it wouldn't actually activate the integrator. Similarly, changing the settings on the integrator would cause something similar. Oh. So right now it looks like it's producing a constant ringing. I'm just going to change the settings slightly on the integrator, and that should make it ramp down or ramp up a bit slower. The settings on this are very fine. Because it's on a breadboard, there's a lot of causes for distortion. So, touching something here has caused it to increase its gain value. There's a sharp increase there. Normally this is meant to be, prior to starting up this video, it was stabilized and ramping up very slowly. Okay, changing the voltage, here we go. Now the ramp up has been slowed down a little bit. I'll just note that this is an exaggeration of what normally occurs when it is at a very fine control point. So right now it's oscillating by about 90 to 100 millivolts above and below the set point. I'm just going to pause the video again and retune it until it's working properly. So I actually just realised that the problem was not the settings or me touching the circuit, but actually the set point itself. I'd set it to 3.7, 3.8 volts, and the voltage at room temperature is about 3.6, so it was way too close to room temperature, and it had no ability to cool since top of this is completely insulated, and it'll cool very fast and it won't heat up as quickly as if it were actively cooling something and working on a load. So right now the output is stabilizing, and the oscillations are a lot less. Just before I changed the settings, so now it's not going to be working quite as right as it was before when I started this video and did the first demonstration. But I just wanted to show it working at multiple set points. Normally the thermometer output would be completely stable at wherever it happens to be. So I'm just going to turn the proportional gain up a bit back to where it was. And turn the integrated gain down. I'm just going to pause the video again and get it working. Alright, so I didn't actually change anything just before. I just poked a bunch of the components around, and I think something was just not contacting the breadboard correctly. Now it is stabilizing, the oscillations in the integrator are dropping, and the overall output is just becoming more stable. So right now it's oscillating about, let's see, 4 millivolts around the set point, which is slightly higher than what it normally would be, which is 0, which it showed in the start of the video, but it's still fairly good considering that it represents a fraction of a degree in change. I'll just note that the peltier is, even though it's a bidirectional device, it's only set up to cool at the moment. The circuit was initially supposed to work both ways, but that wound up being impractical and extremely power inefficient. And it would also add a lot of complexity, since it would need a whole second part of the circuit to be, a whole second PID array to be added to the circuit, since it wouldn't be possible to use analog to just switch over the output, at very least without severely distorting it and making it ineffective around the 0 point, which is where it would switch over. So, yeah. So I've just set the set point to 4.2 volts again, just to show that it normally would be a lot more stable. Right now though, I'm going to switch over the set point voltage out and swap it over with the pulse width modulator, since I don't think I demonstrated that properly. I'm also going to change the time domain so that the pulse width modulation is visible. Alright, so I'm just going to disconnect the PID and make it start the loop. It remodulates, so right now it is, because this is all low, the inverted signal will be all high, so it'll go to 100% duty cycle. And now turn it back on again. It'll be ramping up from here. So again, this is the inverted signal. So a low signal would represent 100% duty cycle, and the more that the duty cycle of the signal increases, the more it decreases on the peltier. So right now it's fairly stable at this point, and the noise is just causing that phase shift that makes it go back and forth. It'll do that even if I have the trigger set up properly. Lastly, I'll just note that because of the power supply, the higher the set point is set, the more stable the circuit will operate. Just because the peltier becomes vastly more inefficient the harder it's run. And at here, between around 4.5 to 5 volts is the upper limit of the circuit with this given power supply. The battery here, as well as also the limits of this particular peltier cooler. A higher power one might work better on a lower voltage supply like what I've got here in this old car battery. Now I'll just try and show some of the other functions of the circuit, just to show how they work. So right now I'm going for the triangle wave as it's added into the comparator. So that's the triangle wave here. It goes slightly negative, but that doesn't impact how it can be used by the comparator, since the comparator supports the voltages going negative, but only in the current configuration. If the inputs are swapped around, it doesn't tolerate the negative there. And the set point you already saw, that was what the channel 1 was connected to the entire time prior to now. And I'll show this as well, the gate signal for the MOSFET. Harmonics on the breadboard cause the gate signal to look like this. Also, this is what the inverted signal looks like. Even with the gain set up very high, it still has this effect where it has sort of a linear ramp up, and I think that's caused by capacitance in the breadboard itself, because that's the only thing I could imagine would cause the ramp up speed to be that gradual. And I think that's it. Yes, I'll show off. Well, the bottom supply here is negative. So channel 1, negative voltage. And this one here is 12 volts, and that the split rail supply works. But yeah, I think that's it. That should show. Oh, I might as well connect this up to the proportional amplifier. Yep. The distortion also reaches the signal on the proportional amplifier. Fortunately, since this waveform is uniform, it doesn't really have an effect, since all changes to the peltier are averaged out over a really long time. But still, I'll disconnect the power now, which will cause the temperature to rise, and now the output is amplified. And then I'll connect the peltier back on again. So again, that distortion is caused by probably the inductive effects of the high current going through the breadboard, since it's drawing a lot of power, and that causes induction or capacitive effects or eddy currents, or I'm not sure what it is. But yeah, that's what it does. These sorts of things normally don't happen on a circuit board unless you choose the wrong resistor values, and I have been switching out the resistor values a lot to try and tune this to get rid of this noise. Also adding low pass filters didn't really help, because if it's an inductive effect, I don't think a low pass filter will work, since it would just ring in the capacitor. Also, the low pass filters cause offset in the voltage, which impedes the actual signal, since this all works. A lot of these voltages are biased and only happen to overlap, because I don't have digital chips capable of precisely setting specific rail voltages in a stable way where one doesn't impact the other. Using more, if I had several linear positive and negative linear regulators where you can adjust the voltage with a potentiometer, so that you can get multiple set points, multiple different rail set points per stage, that would probably work better. Also, this design would probably have worked better using the, I forget what it's called, the 7447, I think it is, or 749, the other op-amp that we have at the university, which has 4 channels instead of just 2. The more channels it has on the one op-amp, I think the smaller and more concise the circuit would be, and the less distortion it would generate. Just having so many wires here and outputting multiple frequencies with this one is drawing several, it'll peak at above 5 amps. So it's pulling 5 amps through these cables, through the breadboard. It's using a separate power supply for that specific reason, but it still has an effect on the actual signal itself, even though it's not impacting the rails. Anyway, that's it for the demonstration. I think that's all I needed to show. Yeah, that's it.